Students. So what do we have? We have lots and lots of machinery and all these little theorems that we've already developed about span and independence, and now we have this definition that combines the ideas of span and independence together, and we can use all these little things to get a whole bunch of results. Now this first result is an important one. It says that if you have any collection of vectors that spans a space, you can make it into a basis by simply removing some vectors. I don't have to take anything weird. I don't have to take any linear combinations of the existing vectors. If I have a collection of vectors that span some space, I can form a basis just by taking some of them out. So let's write that down. So what I'll do is I'll say suppose is a nice word. Suppose V is equal to the span of V1, V2 through Vn. Okay, so V is equal to the span of these vectors. Then some subset of the set V1 through Vn2 through Vn forms a basis. Okay, so that's what this says. You can always just remove some of them to get a basis. I don't have to replace anything. I don't have to put in combinations of these vectors. Just removing is enough. Okay, well, let's prove this. Proof. Well, first of all, if V is the zero vector space with just zero, we're done. Because then we don't need to take any vectors. Suppose not. Otherwise, if V1 through Vn is independent, we're also done. Right? Because then we have a basis. So what do we have? We have the case where we have a vector space which is non-trivial, and it has vectors in it that are dependent. Okay, so what we're going to do now is we're going to do a process. So suppose the only other possibility, which is this is dependent. Well, what do I know? Then I know we can find a Vj, and we've proved this before, so that the span of the vectors without Vj is the same. Okay? So what I'm going to do is I'm going to repeat the process until we get an independent set. Now there's something that needs to be said. How come we know the process stops? Okay, so two things to think about. One, we have a finite collection of vectors, right? So we can't be removing forever, right? But what happens if we never get to an independent set? Does everyone understand that first part? If we had an infinite collection, then we could remove forever and this process would never stop and we'd be in trouble. But that can't happen. Okay, so what's the only thing that could go wrong? It's that we remove, and we go all the way to nothing. We get all the way to the last vector and we remove it without ever reaching an independent set. But that can't happen because a single vector forms an independent set by itself. So because of that, the process must stop. And when it stops, we are done. So, what does that mean? Like I said, any collection of vectors, you can form a basis by just taking a subcollection of those same vectors. And this is something that's going to come up quite a bit. What I should say right now is an immediate corollary, which says every finite dimensional vector space has a basis. Okay, so proof, well, if it's finite dimensional, then what does it mean? What's the definition? Well, V is equal to the span of some V1 through Vn. And what can we use? Well, I know if V is the span of V1 through Vn, then some subset forms a basis. So some subset forms a basis by our last result. So it has a basis. Now, notice when I say stuff like it has a basis, that doesn't mean like I'm claiming that it only has one basis, right? There might be many ways to pick a basis for the vector space, and in general there will be. But it means it does have one. A basis does exist. So don't accidentally try. We have a lot of uniqueness in this class. Don't accidentally ever try to put uniqueness where you don't need it, because otherwise you'll get some incorrect, I don't know, propositions that you might end up believing. But that's it for right now. And we have some more stuff to prove moving on.